Welcome to mini lesson 20. This is the start of the last week of PY 413 for spring 2020, and it's the last new topic that we're going to do. What it is really an application of a lot of ideas that we've already seen, but it's unique enough as an application that if you haven't seen it before, you probably have trouble seeing the point. I think it's a really good application both of statistical mechanics and of thermodynamics. And so I hope it's a really good topic to lead us into studying for the final. I'll be posting a lot about the final in the coming days. So let's get going with the thermodynamics of ideal mixtures. We're going back to section 5.4 of Schroeder for this topic. All right. So let's just take a look at intuition about mixtures. And I want to just think about it almost, in fact, exactly statistically, from the standpoint of statistical mechanics. So if we think about having a collection of 10 blue squares and 10 yellow squares, and let's imagine just sort of conceptually dividing, putting a little dividing line here. There are many more ways to have the squares arranged so that they're all mixed up, random blues and yellows, than having all the blues on the left and all the yellows on the right. So you can think of it as asking, how many different ways can I choose which 5 on the left will be yellow and which 5 on the right will be yellow? And so in this picture I show one of the ways, and hopefully you can see that that's essentially a combinatorics question, which makes it straightforward to do statistical mechanics, right? And so this is basically telling us the true stat-mech origin of the idea that mixed systems are disordered, right? But the word disordered is not really quantitative. In fact, what we would rather say is that the multiplicity of a mixed system is higher than the multiplicity of an unmixed system. And so if we just look at this picture and take that multiplicity idea seriously, we would say you can always increase your entropy by mixing, right? In other words, a mixed system is always more probable than an unmixed system. But we know it's true that not every system mixes, right? So if you take oil and water and pour them together, if you wait long enough, the oil and water will separate, right? And so what's going on? And the answer is the mixing effect that we've described here refers only to the system, right? And so if you just had one completely isolated system, then yes, it would always try to mix. But in fact, the second law tells us that the entropy of the whole universe always increases. So we don't always go to the maximum entropy of the system, right? We go to the maximum entropy of the universe. And so one of the ideas is that in some systems, mixing causes the entropy of the environment to decrease more than the entropy of the system increases. So it's complicated, but this is why I think it's such a good application of thermodynamics, because it really forces you to think through differences between system and environment and the fact that there can be competing effects driving thermodynamic tendencies. All right, so what does it mean to be mixed on the macroscopic scale? In some ways, we're thinking of mixed versus separated as a phase transition in this chapter, in chapter 5, right? And so when we think of a phase transition, we're kind of thinking of a sudden change in a macroscopic variable due to mixing. And so what is the macroscopic variable that we need to describe this idea of mixing as almost like a phase transition? So we know that it needs to have a finite, in other words, a non-zero average value when you average it over all the microscopic degrees of freedom in the system. We know that it should be 0 in the separated state. And so let's let the two components in the system be labeled as A and B. So let's say A is blue and B is yellow. Then the fraction of B, or the fraction of yellow, we'll call it little x sub B. And that's the number of B components divided by the total number of components. So it's just the fraction of B, right? And so this, it turns out, is a good macroscopic characteristic that we can associate with mixing, the fraction of b. So the corresponding definition of x sub a would be n sub a over n sub a plus n sub b. And so if you add those two together, you see that the fraction of a plus the fraction of b always has to sum to 1, right? So now let me tell you what the definition of mixed is, right? A mixed system is one for which almost any macroscopic subsystem would be found to have the given fraction, right? So let's just look at these pictures. If I choose macroscopic subsystems to be the left half and the right half, in both cases I'm going to get x sub a equals a half or x sub b equals a half, right? And so those are valid for any point in the system, right? And I could draw a little circle right here, and up to some fluctuations due to the finite size of the system, roughly speaking, I'm always going to get x sub a equals a half no matter how I choose the subsystem. So in contrast, if I look at this system that's sort of intuitively separated, right? If I choose my macroscopic subsystem to be over on the left side, I get x sub a equals 1. If I choose it on the right, I get x sub a equals 0. And so x sub a is not a constant macroscopic descriptor of the whole system because it varies from point to point across the system. So that's what I mean when I say the system is mixed. It means that that value of x sub b or x sub a is going to take the same numerical value no matter where you choose to measure it. There's a single value across the whole system. So it's just like temperature, right? We say a system has a temperature, right, when you put a thermometer anywhere in the system and you get the same value. If you got a different value by putting the thermometer on different parts of the system, it wouldn't be valid to say the system had a temperature. Temperature would not be a good macroscopic characteristic. Okay. So let's look at the entropy of mixing. This is just a two-state multiplicity problem. I can't remember if we discussed it very much in Chapter 2. I know it is actually mentioned in Chapter 2 by Schroeder, and sometimes I mention it. I think I mentioned it in the context of alloys. But in this case, we're not necessarily even thinking of it strictly as an alloy, which is normally a solid. This can also be liquids and gases or anything, right? But the basic idea is, let's assume we have n total locations at which we can locate two different components, and the components are A and B. And so the number of ways of arranging the two different components is you take your n available locations. They don't have to be ordered. They can be anywhere in space, totally random. And you choose which of the n are going to be B. And that's all. That's the multiplicity of the mixed system. And so let's write out this combination. It's n factorial over nb factorial times n minus nb quantity factorial. And we know that simplifies to n factorial over nb factorial divided by na factorial. So let's turn the crank on our statistical mechanics using the Boltzmann entropy. I'm doing some of the steps here. You need to do this. This is the kind of practice that you need for your final exam. One of the things that I will flat out tell you that I need to confirm is that in going through this course, you've learned how to use this statistical mechanics machinery. It will be on the final. Probably not this exact calculation, but something that's pretty much identical in a different context. All right. So we're going to apply Boltzmann entropy. So we basically need to evaluate the natural logarithm of this multiplicity function. So break out the logarithm by subtracting off the denominator parts. And now let's apply the Stirling approximation. We're going to use the one that we call the version of Stirling approximation that we call baby Stirling. And that's just because we're focused on the logarithm here. So adding the extra correction of natural log of square root of 2 pi n is not important when you're dealing with the log. If you cared about the multiplicity by itself, you'd want to really worry about that, but here it's not so important. So we apply Stirling's approximation. We get n log n minus nb log nb plus nb minus na log na plus na. All the little NAs, NBs, and cancel with N, right? Do this yourself. You just got to get used to how this is going to go because it happens this way in so many different problems. If you're not, if you do it over and over again, it'll go fast and easy. And if you've forgotten that these things often cancel, you'll be a lot slower and you may mess it up. Okay, so with all those cancellations, we just get n log n minus nb log nb minus na log na. So now I'm going to stop doing the steps for you and ask you to do it yourself because watching me do it doesn't help you that much. But I'll tell you what I want you to do. I want you to substitute for n sub a and n sub b in terms of x sub b and n. All right? These are the only two variables that I want to be in the final formula. So I need you to substitute here and here in terms of these two variables only. And so the final result that you get for the natural logarithm of the multiplicity is that it's equal to the negative of n times x sub b log x sub b plus 1 minus x sub b log of 1 minus x sub b. Again, really good practice for the final. You want this to be something that is easy for you so that you get all the credit for doing this good work on the final exam and don't let it eat up all your time and energy. Okay. So the basic idea here is we now have an expression for what's called the entropy of mixing, right? So we'll put back in the factor of Boltzmann constant that's needed in the Boltzmann definition of entropy. You get the entropy of mixing is negative n kb times this quantity from the last slide. So the important thing to note about this is because x sub b is always a number less than 1, right? It's a fraction of the total available sites occupied by b. The square bracket expression will always be negative, right? So natural log of a number less than 1 is a negative number. Same as the natural log of 1 minus a number less than 1. So everything in here will always, always, always be negative, not possible to be positive. And so the entropy of mixing, because of this added negative sign out front, will always be positive, right? And so there's a clear conclusion here. Mixing always increases entropy. We could see that clearly intuitively from the very beginning, but now we have a quantitative analysis that shows us by exactly how much mixing will increase the entropy of the system. Okay? So let's now analyze this in terms of Gibbs free energy. And the reason for that is that we know not everything always mixes. And we know that this is going to be somehow connected to the fact that the entropy of mixing that we just calculated is for the system, but what matters is the entropy of the whole universe. And the way we typically deal with the entropy of the whole universe is by not talking about entropy anymore and by transitioning our language into one or more of the free energies. And so for mixing situations, we're almost always interested in Gibbs because we're going to be at situations where we have independent variables of pressure, temperature, and particle number. Gibbs is the potential that has those three variables that are relevant to us. So let's start out by saying that each of the components has an individual Gibbs free energy per molecule when it's isolated and we're not worried about anything like mixing or interactions, okay? So I'm doing things in terms of per molecule here because that's what Schroeder does. Essentially, Schroeder wants us to stop having little or annoying factors of capital N carried around everywhere. So explicitly what I'm writing here and for the rest of our discussion of mixing, both in this lesson and the next one, is Gibbs free energy per molecule. Right, so Gibbs of component A has an enthalpy of formation and an entropy of formation. So for example, if you were given a material, you could look up those values in the back of your Schroeder textbook. Since you'll be doing open book finals, that would be something that you might end up having to do. All right, so, and then the Gibbs potential is defined as enthalpy minus temperature times entropy. And I should say, since this is a Gibbs per molecule, H and S are also defined on a per molecule basis. In other words, if you had an expression for those functions in terms of N, we would be letting n equal 1. And so then the idea is that if no mixing happens, the total Gibbs free energy is just equal to the Gibbs free energy of A times the fraction that's in A, that is occupied by A, plus the Gibbs free energy of B times the fraction of B. So we can write that whole thing out in terms of just one variable x sub B, right? Because x sub B and x sub A are not independent. So just write out the whole thing in this way. And so what you have is a linear function of x sub B. And I've plotted it over here with the basic idea that, let's see, G0A is equal to 2 electron volts, and G0B is equal to 5. So you can plug that in. When x sub B equals 0, you get G is equal to G0A, and that's down here. And when x sub B equals 1, you get G equals G0B, and that's 5. And then the formula linearly interpolates between them. So this is pretty boring, right? This just says if you have two things that are not mixing, they just act like they're independent of one another, and they add their free energies together according to the number fraction. And so the idea here is, and this is something I'm going to say repeatedly for the next few lectures, is not really that you're imagining changing x sub B to move along this curve. That's not how you use this curve at all. The way you use this curve is somebody tells you, I have x sub B equals 0.4. Tell me the free energy of the whole system. And you would go up here and you would say, it looks like it's about 3. Right? So that's 0.4 times 2 plus 0.6 times 5 equals about 3. Okay? So you're not thinking about, okay, let me change x sub B from 0.2 to 0.7. What happens? That's really not how this ever works. Be careful not to think that way. It's sort of tempting when you see the plots. All right. So if we now allow mixing of the components A of B and nothing else, that's going to be the definition of an ideal mixture, right? Then we take that same linear function that we just had and we subtract off T times the entropy of mixing, right? And so the basic idea is that the entropy of mixing contributes to the entropy factors that appear in the total free energy. So it's going to, oopsie. So it's going to pick up a factor of T and get multiplied through to, I mean, partly it's to give it the right dimensions, but we know that in G, you know, all the entropy factors get multiplied by T just in the definition. That's how you do the Legendre transform. All right, so let's plug in our formula for entropy of mixing. I need to point out again that following Schroeder's notation or ideas in chapter 5, section 4, we're doing everything on a per molecule basis. So I set capital N equal to 1 in developing this entropy of mixing formula, so it doesn't appear up front anymore. So we've got our old formula, which was just a linear function of x sub B. We've got a KBT, where the KB came from the entropy. And then we've got this XB, log XB, etc. That's a very complicated function of x sub B, not just linear anymore. This equation is very important. This defines the behavior of an ideal mixture. Okay? So ideal mixture means we have two individual components that determine the linear behavior of the function. And then we have an entropy of mixing, but we don't allow the components to interact or see each other in any other way other than just acknowledging that they will have an entropy of mixing. Right? So the other thing you have to note is that in the square brackets, once again, we're always going to have a negative number. Temperature is always positive, so we're going to be adding a negative number to our initial free energy linear expression. So mixing is always going to lower the free energy. That's exactly what we said before, where it always looks like mixing is going to be favored. And in this free energy expression, indeed that is true. In an ideal mixture, ideal only, mixing is always favored, right? So for example, what that tells you is oil and water do not constitute an ideal mixture because they actually don't mix under most conditions. So how do we use this expression? Again, this pretty nasty one, right? And so the typical analysis is that someone gives you a value for x sub b, and that's your value that you need to analyze, right? You don't need to think about x sub b moving along curves, right? And so again, your boss might say, I would like you to mix 3 moles of water, that's component A, and 2 moles of alcohol, and that'll be component B. So here's this meme of the typical boss who would say that to you. Probably never mixed any water and alcohol in his whole life, right? Stinker. So what we need to do now is compare the two curves, the unmixed curve, which is blue, that's just the linear part of the function, and the mixed curve, which is the linear part plus the entropy of mixing part, okay? And so at xb equals 0.4, that's the problem that we're given by our stinker boss, right? We need to ask the question, will it mix? And the answer is absolutely yes, if it's an ideal mixture, because the red curve is always a lower free energy than the blue curve, and therefore the red curve will always be the thermodynamically favored state of the system, okay? And so we're not imagining that we're going to try to mix 0.4 moles and it's somehow going to change along the curve. We're actually comparing values along a vertical slice. That's the most typical way to analyze these curves, all right? So once again, for an ideal solution, mixing is always favored. But it is important that the size of the free energy lowering due to mixing depends really significantly on the temperature. So if you're at really, so let me see, on the one I just showed you here, I did a temperature, I think, of 1 electron volt, so kBT equals 1 electron volt. And on these, I'm showing some different temperatures. So at much lower temperature, there's actually very little distinction between the red curve and the blue curve, right? And it basically says that the mixing effect at low temperatures is really a very minor free energy lowering compared to the unmixed state. Whereas when you go to really high temperatures, the mixing effect is a huge lowering of the free energy. It depends on the composition. It depends on the temperature. This is a really important general idea. This is not just applicable to mixing, and it's not just applicable to ideal mixtures. At low temperatures, the entropy effect is relatively small, and at high temperatures, it's relatively larger. So at high temperature, entropy tends to be dominant. And you can kind of see that here if you just look at the free energy expression. There's always this temperature multiplying through the entropy, right? And so as the temperature goes up, this term is going to be more and more and more dominant. And that's a general intuition that you want to carry with you forever. At high temperature, entropy effects are dominant, basically because G equals H minus TS. And so if T is large enough, TS will always be the dominant factor. All right, so the thing I want to say is ideal mixtures are an important conceptual starting point. They're quite rare to find in practice. And so in the next mini lesson, what we're going to do is add on additional effects, interactions between components A and B that allow us to talk about real mixtures that we would find in the lab. So we'll see you next time.